Hello again and welcome back to Advent of Code 2025 in MIPS assembly for the PlayStation 2. Today we are up to day number 8, and this is probably the most interesting day of the days that I completed in assembly. And aside from day 2 where I went completely the wrong direction and made it much harder on myself, the most involved. So what do we have this time? Day number 8 is called Playground. And let's see, we've come to a playground, setting up Christmas decorations. We've got some electrical junction boxes. And these junction boxes are all with coordinates in 3D space. So X, Y, Z coordinates. And then they're like, hey, we want to connect pairs of junction boxes that are as close together as possible according to straight line distance. So you start with the ones that are the closest together. You connect them and they become a circuit, the same circuit. Now after connecting them, there's a single circuit with 2 junction boxes. Right, and the remaining 18 are in their own individual circuits. And so what you want to do then, now the 2 junction boxes that are closer together but aren't already directly connected, so you go and get ones that are not closer together but not connected, and you connect them together. If it turns out that you end up connecting into an existing circuit, now you've got a circuit that's got 3 junction boxes, right? You keep doing that, and for part 1 we want to keep together 1,000 pairs that are the closest together, and then we multiply the sizes of the 3 largest circuits. So once we've connected 1,000 pairs of boxes together, we multiply the sizes of the 3 largest circuits, and then we keep going until they're all in one large circuit. And we want to then multiply together the x coordinates of the last 2 junction boxes that we had to connect to make it a single circuit. And we get these values here, which are relatively big. Well, it's reasonable size here. You see, the big problem on this one here is the size of the input, because we have a lot of things in this input. No, not really supposed to show the input, but hey, there's a lot of numbers, a lot of positions in this input, a lot of junction boxes, and we have to find like the closest ones together and do the closest ones first, which means we need to sort of order them. We need to do a sorting. We have a sorting here using the straight line distance, and you can look this up, which gives us the Euclidean distance here, right? So I work out the Euclidean distance 3 dimensions, right? It's here p1 minus q1 squared plus p2 minus q2 squared plus p3 minus q3 squared, and then you take the square root of that and you get the distance. Now that seems like a big problem, because running on the PlayStation 2 we have single point precision floating point, or single precision floating point unit, which is not accurate enough for this, and so that would turn into a real pain. But there is a trick, right? If you actually want to work out the actual distance, like in real units, say you've got the positions and then you want to have how many meters or whatever is between these 2 points, right? Then you need to do the square root. But if all you need is to order them from the largest distance to the shortest distance, all that square root does is compress the distances. It doesn't change the order. So you can skip the square root part and just do those multiplications and addition, and you'll still end up with the distances in the same order. And so that's how I get around this little issue here. I don't do square root, and so that means that I can sort the distances. I can both calculate and sort the distances just fine. So that's what I'm going to be doing. Let's have a look at what's going on in my code. So I'm very familiar now. We've got four things up here: junction list, distance list, and circuits. We've got a circuits len here. That's just it's not a list, it's just a single value that's there, and circuits is a list of lists, I believe. That's alright. So our normal start off here, right, we're going to clear out the junction list and the dist list pointers, or the lengths at the start of those lists, which effectively clears them. The data's still sitting there, but it won't be in memory anymore. It won't be used anymore. And we have this loop here that's going to clear out my circuits, because it's a list of lists. Every list in there has a length, and so I have to go through the list of lists, clearing the length of every one that's in there already. Right, so that's what's going on here. I've got this value here, 4016. I think I basically said, well, the max size for a circuit, or the biggest circuit, is going to be 4016 bytes in memory, essentially. And so that's, or 4000 bytes or something, somewhere close around there. And so that's that's how I've spaced my lists in this list of lists. And so, yeah, multiplying by that to go to each position in memory and clear out its length. So go through that loop, clearing those out. And then I clear out ASCII num as well, because you need to clear that up. Then we set up our input beginning and end, and we have this ingestation loop, right, where we're checking if we've reached the end of it, and if we are, we bounce out. Otherwise, we see if it's a 0 to C, which I believe is a comma here, right? And if it is, then we go to convert num, or if it's an OA, which is a new line character, we go to convert num. I think I didn't mention it, but this S5, I believe, is tracking which position in we're at, sort of thing. So S5 is 0 for the first value, 1 for the second value, 2 for the third value, essentially. And so when the third value is put in, we then say, well, we're done with this box, this junction box, move to the next next junction box, sort of thing. We'll see in a minute, don't worry about it. So if it's not one of those, we convert the number and put it into ASCII num, the ASCII num list. We have an increment for the ingest loop. If we're converting our number, we go into here, we check if it's a 0 length number, in case usually the spare line, the empty line at the bottom, will cause this to happen. If it's not, we can convert ASCII. We store 0 back into ASCII num. Load S1, we load out the junction list, load with S3. If this is equal to 0, then it's the very first junction, right? We haven't stored any other junctions before, so I just jump into this first junk here. If it's not equal to, if S5 is not equal to 0, we go to store junk. So I mean, I guess this probably is not necessary, really, because the first one should also be, no, maybe, yeah, because the first one should go through this anyway. So if we're on the first junction, you know, we add S3 here, we add one to S3, and we store it back in. So that's the length of our junction list. So we're only incrementing that whenever we actually hit this part here. So it's the first time in, and whenever S5 is 0, we increment this. Otherwise, we multiply it by 4. Each value is up to a 32-bit number, so that's what we do there. We multiply it by 4. Oh no, wait a second, because we're shifting it left by 4, so it's multiplied by 8. So that gives us space for a 64-bit number, I think. But I think that's just multiplied. No, it's not multiplied by 8. It's multiplied by 16. It's multiplied by 16 because each junction is going to take up. I need 3 values in it. I've decided to use 3 words, which gives me 12 bytes essentially. And so I've decided to throw away the last 4 bytes and just space every junction, or every junction box's coordinates aligned with 16 bytes. So there, that'll take me to the first place for putting in a junction by multiplying by 16. We add that to S1, which is our junction list thing there. So that gives us the memory location. Then I use this value that's in S5 and I multiply that by 4 by shifting it by 2 and add that onto it as well. And then we store the word that we just converted into the list. Then we check what the value was. If the value that led us here was a comma, then we go back to the ingest increment there, and we add an extra, and we add 1 to S5. If it was an OA, then we go back to the ingest, but we make S5 0. We put a 0 into S5. Right, so that's it'll go through all of those numbers here, and it'll make that big list of junctions. And then we go into these 3 sections here, which are going to solve the rest of the problem for us. So we have the convert ASCII here. That's basically the same as before, I think. No real changes in this. We're still using the shifts to do the multiplication and addition here to add to make to do multiples of 10. Calc distances. So I've got 2 loops here because we have to calculate the distances between every node. So the first node and every node after it, the second node and every node after it, the third node and every node after it, the fourth node and every node after it, right? They all have to be, all those distances have to be calculated. So we load up this junction list, we load up its length, I subtract 1 from that length, which gives me the final position in the list, I believe. Then we go into this junction list here. We've got this, well, zero dist list, outer dist loop, and inner dist loop, right? I think I'm reusing some of these registers, which is why I load up the junk list here again into S0. Clear out S3. We shift S6 to the left. We multiply it by 16. We add that to junk list to get the address, right? And we do the last S7 as well. Add that as well. So we're now actually pointing at those positions. Load out the words, the first words, right? We subtract the first one from, the second one from the first one. Then move it into S2. Now do this parallel multiply word. I believe what I'm doing with this parallel multiply word is that I essentially get out a 64-bit result directly into S1. Let's just check that up again, shall we? Do I have this? Try to remember now which one. If I have it, if I have the window capture, let's see. Let's grab. Not you. This thing here again. Okay, so we've got the instruction set again. It was the parallel multiply parallel word. Yep, here we are. Right. This looks like the right one, I think. Parallel multiply word. Multiplies bits 64 to 95 by the bits of 64 to 95 of RT and RS, like those ones there, and bits 0 to 31 with bits 0 to 31 as well, and assigned 32-bit integers, and stores the 64-bit resulting 64-bit value in the RD, the corresponding words shown in operation. And I don't have, here we go, we have an illustration of it here. Right. So you're multiplying this part here together with this part over here, those parts into there, and you end up in your result in this RD here. So you can get this if you have a 32-bit number here and a 32-bit number here, you can end up with just a 64-bit number straight away in your register, which is more useful than the other mults that we have in this. Actually, if you do a multiplication that I actually shot here, you end up with a 32-bit value in your destination register here, the RD. And if you want the 64-bit value, you have to pull it out from the high register, which is kind of annoying. What happens is that if you in the RD one, you end up with sign extension, which is a pain. But that's alright. So yeah, this parallel multiply one is actually a little bit more useful at times. So we get that that multiply there, comes back out into S1 there. We add it to S3, that sort of distance that we're building up. Then we do that for the next. So we've done like the X positions. Now we're going to multiply the Y positions. We subtract them from each other, and then multiply them and add them. Remember, we're doing the multiply because you're supposed to square the result. I guess you probably don't actually have to do that to get the relative distances, but okay, fine. I'm not going to go back and redo it now. I can probably take them out and test it. We add them to that result, and then we do the z coordinate, the same sort of thing. Subtract, multiply by itself to square it, add them together, and so now we've got a distance, and it is a distance that is comparable between junction nodes, between pairs of junction nodes. Right, so what we're going to do now is that we're going to store this into this distance list. So we load up the length of it. We're using double here because it's going to be quite a long list, really. It's probably not millions, but it's quite a long list anyway. We add one to it, store it back in. We multiply it by 16. Again, they're going to be 16 bytes per entry in this list. We add that onto our pointer up the top here, and we store this double, the S3, which is our distance between the two nodes, and S6 and S7, these are the positions in memory where you say pointers to the junction list of where these two nodes, right, of these two junction boxes, where they are in memory in that previous list. We're storing those in here as well, because we probably need them for the next parts, right? So first we subtract 1 from S7, and then we loop this in a loop until it is 0, and then we add 1 to S1, or load, well, we load S1 with 1, and we add so I'm checking if S6 is 1 in the end. I'm not looking for 0, I'm looking for 1. So we add a 1 into there, subtract 1 from that, and we branch not equal to 1. So I mean, I probably could have done like a set less than or something instead. It's fine, it works. And then we finished up with this thing, right? So that's calculating the distances. Next we have to sort the distances. And so what I've done, like what I've already in the past implemented something like a bubble sort. I went straight for bubble sort first because it's dead easy to implement. Too slow. Way too slow. Bubble sort is way too slow on this list. It's going to take hours, days maybe to get through it. So as you can see on screen right now, implemented a quick sort, and there's a lot of algorithms you can find online for how to do quick sorts. I looked at one because obviously off the top of my head I'm not writing quick sorts every day, so I wrote a quick sort in assembly here. So we've got our sort distances. We're going to load up the distance list pointer here, and we load up its length, multiply that 16. We have that there, so we're in that first position in the distance. No, wait, we're in the last position in the distance list. Sorry, in the last position. No, wait. Yeah, we're in the last position. Is in D7, and then we jump to quicksort, and we move this into the first position. So S6 is the lower bound, S7 is the upper bound, and so jump into quicksort here, and you see this is our way out at the very end. We load RA and jump to RA to get out. So we jump into the quicksort thing itself. Say I've got a thing here, it returns in S5, it returns S5, that's right, whatever. Back up a bunch of registers. This is recursive, so we do have to back up, especially like the RA, the return address, because we're going to end up, having a lot of things in memory. So just set less than. So if S6, the value in S6 is less than S7, and these are address positions, right? Not the distance. We're not checking the distance here. If the address position is less than S6 is less than S7, then S1 will be a 1, right? If S1 is equal to 0, which means that S6 is greater than or equal to S7, then we jump to quicksort end, right? So S7 is probably going to be working its way down towards where S6 is. So S6 is kind of like what we call the pivot point or whatever. Otherwise, we load the value that's in S7. We load double at S7, so it's going to load the distance. We subtract 16 from S6 and put it in S5. We load the distance from S6, and we do another here, set less than. So if the value in S2, oh, sorry, I just undo that. The value in S2 at S6 here is less than is the value that's at S7, it'll be a 1. If it's not that, if it's not a 1, it's not less than, then we skip the swap here. If it is less than, then we will add 16 to S5, so we end up in this position here, this same S6 position, and then we swap S5 and S6 around, the values at S5 and S6 around. right? We just swap their positions around. And then we add 16 to S6, so we move to the next value in the array, right? And we do this again, and we loop back up. So long as S6 is not equal to S7, we loop back up. So S7 is not moving. S7 is the one that's not moving. Sorry, S6 is the one that moves towards S7. So basically, like any value of S6 that is less than S7 gets pushed down until only values that are above greater than S7 sort of remain, and then S7 gets like swapped around as well, right? Because once we end out of this, like once we fall out of this, and we no longer cross that, we then go here and we swap S7 and, well, I have S5 here, but it's probably going to be the value that's in S6 essentially again, or one above the one that was last in S6 or whatever. No, wait, no. S5 you can think of as tracking the position that was last moved, that was last exchanged, right? It's kind of hard, like in my head again, to remember exactly what's going on. But so, right, S5 is like the position that we last sort of, the last position we sort of moved. S6 is like a test position, and S7 is what we're evaluating against, right? So S6 we're testing all the values that are before S7. S5 is like where we've last shifted something into, so that trails behind. And then once S6 reaches S7, all the values that are behind S5 are ones that are less than the value that was in S7. So then we can put S7 we can move S7 onto the top of that list. And what we sort of have there is now, like, it's not a sorted list, but we know that all the values that are below there are less than that value, right? And all the values that are above it are higher than that value. So what you then do is that you load another quicksort, right? We load out those values from S6 and S7 out of the stack again, which were our like beginning and end of the entire list pointers sort of thing, I think. Did I save them in there at any point? Don't think I did. And then we subtract yeah, you need to load them out because you need them for the different ones, right? So I load out S6, so S6 goes back to what it was, but then I add I subtract 16 from S5 and I make that S7, and we jump to this quicksort here. Then the next time we load out S7, so it was what it was when we came into this iteration, and I add 16 to S5 and put into S6 and jump into another round of this quicksort. And so yeah, you're dividing it up progressively more and more and more until you run out, until you can't do anything anymore. And at that point it's all sorted, and you just end up falling out of this whole quicksort engine. So that sorts our giant ass list. It's not that long really, right? When we look at it, this quicksort is where are we? 75 lines in total in assembly. So that's, it's not very long. It does a pretty good job of sorting the whole thing out. There's one thing that I should mention here. That's what I'm doing. I'm doing load quads and store quads. One of the few operations you can do in that like really does the whole register. You load up a whole 16 bytes into the register in one go, and then store it out in one go as well. right? So that's because of course I've got a double for the length and 2 words, a double which is 8 bytes and 2 words which are 4 bytes each for the pointers to the junction boxes. So yeah, those quads. Okay, so the last one that we'll go into is the circuit builder here. Right, so we've got the dist list again. Now the dist list is completely sorted, so we can go, we've got them in order, the pairs that are the closest to each other, right? Simple. We can just go through the list in order. So we load out that list, we multiply it with 16. Again, each entry is going to be 16 in that list. We add that together. We add 16 to the beginning of it, so we get past that length value. S4, S5, check gold, check silver, check gold, 0 and 1. I think it's because I'm going to be checking if this one hits like 1,000, and then you check the silver result, and then S5 is something else. Anyway, so we've got this loop dists here. Oh, I undo that. A load of word out of, see, these are the circuit, right? These are the circuit pointers, the 2 words. So they point to the 2 junction boxes. I do this jump to add to circuit. I do a branch equals, so what comes back, S2 must come back from this add to circuit. If it's equal to 0, then we do the skip con. We branch to the skip con. We add one to S4 and one to S5 in each of these. If it's we always do this, always come back here because this only branches to it. So this adding to S4 will always occur because it's in the branch delay slot here. The one from S5 only occurs if this is not 0. Right, so S5 only increments if this is not 0. We go here, we load S2 with 1000. Probably using it another, yeah, I'm using it up here anyway. If it's not equal to, if S4 is not equal to S2, then we skip silver. So once S4 is equal to S2, we'll do this jump to silver result, or JAL, so we'll go there and come back. If it's not, we skip silver. So that should occur only one time. Otherwise, if S5 is not equal to S2, then we branch to the skip list loop dist next. Otherwise, would end up jumping to the gold result and then come back and jump to the circuit builder end. I don't know why I do this as a JAL instead of just a J, and then I could jump to circuit builder end anyway. Whatever. just whatever. Loop dist next. I undo that. If it's S6 is not equal to S7, we're going to go back up here, and in the branch delay we add 16 to S6, and we've got the circuit builder end right here. So add to circuit here, right? It says here return S2 0 if pair in the same circuit. So if we've got these 2 pairs that I'm evaluating the distance already, and they're already in the same circuit, then I return a 0. Right, I haven't made a new connection because what we have, what is it for silver? I think it was silver. Is it silver? Connect together 1,000 pairs of junction boxes which are closest together. No. One large circuit. The first until all the junctions together, they're all in the same circuit. I'm not entirely sure. 5 S2. I'm not entirely sure how this works out, but I mean, I'll keep going and see if we get there. Anyway, if it becomes explanatory later on. So I didn't put very many comments into this, so I have to go off memory of what I was doing. So, okay, we're into this add to circuit, right? We've got the circuit's len. Remember, it's the length of the list of lists. We load that out. If it's 0, then we go into a new circuit, right? If we don't have any lists yet in our list of lists, we're definitely making a new list. We're making a new circuit. If that's the case, right, that goes straight to new circuits. Otherwise, I go into circuits here. We've got a multiple here of, remember they're all spaced 4016 apart. So I'm going to have to search. I'm going to have to search the circuits to see if there's a circuit where one of these junction boxes is already a part of. Because if there is, then we have to add it to that circuit rather than making a new circuit, right? So we're going to loop through the circuits. Right, we're going to loop through these circuits. We load the length out of it. If it's 0, so the circuit has a 0 length, then we go to the next circuit immediately. Multiply it by 2, because I think I'll multiply it by 4, because I think we're just using words for these circuit like things. Because each value in these circuit lists is just the address of the junction boxes again, right? We're just referencing everything back to that junction box list, right? So in this case, they can all be words in length instead of doubles or something like that. Like, don't worry about it. I think they have to be a double in size in total. But I'm loading a word over here, which is the pointer at the beginning of it. Look, I'm not sure what's going on. Everyone probably knows what's going on. Let's see if I can figure it out. So I'll do a multiple here. It's going to be multiplied by 8. It seems a little bit odd. Oh no, right, because each value in this list of lists is just a single junction box pointer, right? So a circuit, so each value in this list is just a word in length, right? Unlike before where I had packed words and doubles in the same list. This is just each value is a word in length, so we can use the words here. So yeah, so what I'm doing with this circuit here, right, I'm going to check if these either S0, S1, I think S0, S1 were the two values, where were we, over here, right, that were loading out of the distance. We check if either of those ones is in this circuit. Right, we check against S0 here and S1 here. Right, we go to, and if they're not, we go into here. Otherwise, if one or both are in the circuit, we move S6 into S2 here, or S6 into S3 here, right? It's like, wait, we found one, at least one in the circuit in this position, and this sort of only works here because like it makes sure that there's only one junction in one circuit. If it was possible that you had more than one junction in a circuit, it shouldn't happen. Then this would not work, but this will end up being fine, I believe. And so then we keep going through the circuits. So we have to go through all of these circuits to see if this works out. And what will happen in the end is that S6 will have, or S2 or S3, which started off as zeros, will have a value that's either not 0 or they will be 0, right? If S2 is not equal to 0, then we go, oh, we've got circuit A, we jump there. If S3 is not equal to 0, then we go, oh, we've got circuit B, we'll jump there. If both are 0, then we go to a new circuit, right? We're making a new circuit, right? Because like S0 was checking one junction, S3 was checking the other junction. If neither of those are in a circuit, we're making a new circuit. If only one of those was in a circuit, then, well, we're going to see what happens here, right? So let's say that the first one was in a circuit. We also check this thing here. Actually, you've got this here, which is an invalid circuit thing. Like, if both are inside the same circuit, then we do this invalid circuit thing. We're not doing any circuit joining or whatever. We just invalid circuit. Fine. If S3, so if we're here, S2 was in a circuit, S3 is not 0, but it wasn't the same as S2, then we're merging two circuits together. So we'd branch that merged circuits one. Otherwise, we just add S3 into the circuit where S2 was, right? So, well, not S3, it's going to be S1, but fine. We load the second circuit into we load the second junction box into the circuit that the first junction box is in. Right. So we load up the length of it, we increase it by 1, we store that, we move the pointer, and then we add it into that end, and we jump out, add circuit end. S2 is not to 0, which is what we want, I believe. Right? S2 is used in here, so it's not 0, which is what we want to happen. We do this one here. S2 here has to be 0 at this point. So if we got circuit B, we can only get here if S2 is 0, right? So we know that S2 is 0, so we're adding the first circuit to the second, the first junction box to the second junction box circuit, right? So the opposite as before, basically the same as this one here, but without these checks at the top, because they are not valid. Otherwise, we're merging these two circuits together. So essentially, because none of the junction boxes can be joined, all I have to do is get the length of I'm not sure why do I need to do this, because I did a multiply here, I guess. Anyway, I don't know. I think they end up spacing it along too far or something. We load out the lengths of the two. Well, we load out the two. Wait a second. We load the word there. From S2 and S3. So we load out the lengths of these two lists. We multiply that one by 2. By 4, sorry, into S6. We add S1 to S0, and we store that back into S0, and then we store a 0 into the second there. So the second circuit has its length zeroed out. The first circuit has its length added to. and then we add that S6 to S2 here, and we shift this one here, what was it, S1, multiply that by 4, and we add that onto there, right? And we do a shifts, whatever. We shift that pointer as well. Move that to the end or something. There, yep. So move that one to the end of it, I think. And then we go and just load words. We load words out of the second list and we put them into the first list. And then we're going like from the end, I believe, right? Because we do the addition here. Okay, I think I see. Right. So essentially, I'm moving along the pointer on the first list to be where its end will be once they are fully merged together, and then I'm filling it in backwards. So it will stop essentially at the end of the existing list of numbers, whereas S7 will start from the back as well, and it moves until it gets to the very beginning of it, right? Because it's going to branch as long as it's not equal to S3, which was the starting position, which is actually where the length was stored. So once it gets to where the length was stored, we bail out of this loop. Apparently S2 is not 0, so we let it pass again. And then we jump to circuit end. If we end up on the invalid circuit, then we set S2 to 0, and we branch to circuit end. And then we have this thing for a new circuit. We get the circuit's length, we have to load its length out, we add 1 to it, we store it back, we load circuits, we add this thing here, we do a multiply, so we move down to the very end of this list of lists, and then we store those in, and then we go to the add circuit end, and this is done. So essentially this thing here should only occur like one time, I think, and that's here when you've got two lists that are the same. Or does it happen more than once? No, because we do additions in there. I don't know. We've got to see how that works, maybe. Anyway, so once we get to the end there, right, that's going to go through all of the lists, all of the distances, and add them into circuits. So when S5 is not equal to S2, we go to the next one. S5 here is 1. So it's only when S5 is equal to S2. Remember, S5 comes out as, or S2 comes out as the result of this. But then I load S2 to that. Oh no, that's only if we wait. If that is equal to 0, then we skip con. We jump to skip con and we add 1 to S5. I'm kind of struggling here to understand why or when or how this actually works out, because we're going to add a whole bunch to, right? So when that's equal to 0, well, whenever it's not equal to 0, S5 will go up by 1. but S2, I mean S2 can be 1000 here. I think, okay, I think if I remember correctly, there is 1000 junction boxes in the list, or 1001 junction boxes in the list. So this will only go up as junction boxes are added to circuits, which means that once all the junction boxes are added to circuits, gold will be about 1,000. Gold will be 1,000, which is how this check here works. So once all the boxes are added to circuits, which is also once all the boxes are in the same circuit, S5 will be 1,000, and that's how we it does this check here. That's how this check here actually ends up working. Okay. Yeah, I believe that's right. So then we go to the two result things. Okay, so what have we got for the results? Let's see, the silver result, backup registers. We go for the circuit's len here. We load out its distance, we subtract 1 from it. We take up this here, so we're going to multiply, add our circuits, we add 1 to there. So what is this? Again, we want to know the sizes of the 3 largest circuits. So I load up, these are going to be my 3 largest circuits. I load up S5 with the length of the list in S7 of the current list that we're looking at. We do set less than S1 S5. So if S1 is less than S5, this will be a 1. If it is a 1, if it's not equal to 0, we branch to bigger circuit. If it's not less than S1, or if, sorry, if S1 is larger than or equal to S5, then we'll go down to this check here. We do the same thing with S2, and do the same thing with S3, and then we do we jump to silver next, which is falling out the bottom, and then we've got these references over here. So depending on where we jump to, it will do either big circuit, just this one here, or it will do bigger circuit and big circuit, or it will do bigger circuit, and big circuit, right? Which is what we do is we put what's in S1 into S0, we move what was in S5 into S1, and we move what was in S1 into S5, and then we go down to this one here and we move what was in S2 into S0, S5 goes into S2, and S0 goes into S5. And then the same sort of thing here, S3 goes into S0, and then S5 goes into S3. Now essentially, this one here is not needed. Really? I don't really need that one, do I? You get rid of that one there, because you just take S5 and put it into S3, because it's, yeah. So that one is completely unnecessary. Anyway, but we're swapping, you know, we're shuffling the length, the values down, so we end up with the largest values in those 3 registers there, 1, 2, and 3. Alright, and then I just do a couple of quick multiplications here. Multiply S1 by S2, and then multiply, and the result comes down to S1, and then we multiply S1 by S3, so we multiply those 3 together, the result in S1, and we store that into silver res here. The result, as you can see, is small enough. I don't have to worry about blowing beyond 32-bit numbers. And so the gold result, here's the gold one, it's even shorter. We go to the junction list here. Trying to think of how we actually, what we do here, the x coordinates of the last two junction boxes you need to connect. So I load up this, undo, I load up this junction list, there is 2. We shift that, multiply it by 16, we add S2, S0 there, we load S1, or we shift S1. Right. So remember, gold result, where were we? Circuit builder, where were we? The merged circuits, no, we're further up, weren't we? Partition loops, quicksort, end circuit builder, here. Right. These values, S0 and S1, they're still held in memory at this point. They're still in those registers at this point. Like when we take this jump, this gold result jump, S0 and S1 are still intact, right? So I have their memory positions already, and I can load them out. I believe, right? Oh, undo. Yeah, here, right? So I multiply that by 16. Is that right? It may be an offset. It may have been an offset in that position rather than the actual address itself. That's what I feel like. Because now I'm multiplying it by 4, so it must be the index I was using rather than the memory position itself. At least that's what it feels like. We add those onto here and do the same with S1. Now I load out the 0 position, which is the x coordinate from each one, and I multiply those together using this parallel word multiply, because that gives me a 64-bit result straight out into the return register here, and then we store that into gold res there, and that's it. That is all of the code. So let's run this. Let's see, let's bring this one here up. There it is. We've got that result there. Let's run it, unpause it first, and it takes a second and it's done. There we go. And the result, 122,430. That's right over there. And the result for the gold one, if I want to count down, what are we? I really should have put commas or something like this. 8,135,565,324. That is the correct one there as well. Right. So it takes a hot minute to run this result, which is not too surprising because it is quite a long thing to calculate. Right. You've got a lot of things in memory this time. So seeing we have a nice nice thing to go over this time, how about we look at the memory? So let's bring up the debugger, shall we? Bring you up over there-ish. Let's make you a little bit smaller over this side here. That's all right. Take a bit of space. It's fine. So this is my standard position in memory. My inputs coming over here. Checking my inputs values, the results, silver and gold, and then this is where the ASCII num comes in at 100, and here is my first junction list, right? So this is the length of the junction list, it's 3E8, and you got these 3 coordinates, X, Y, and Z, right? So I've got this big long list here of junction boxes, positions, and it ends up about there, right? And then at I think about 25,000, we have this list of distances, and you can, I think there's distances. Yeah, you can see that these are all increasing numbers. This is an ordered list because of was solved already. You can see this is quite long. It is 7, 9F, 2C in length, which if I bring up a calculator, which you can't see, but that's alright, which if I check that in hex, what is it? 9F2C in length, it is 499,500 entries. A cool 500,000 entries in this distance list. You can imagine it goes for quite a long ways. If I block this off for a second, where is the thing in memory? Circuits len is sitting over here at 9F FFF0 and starting at A0 for. Let's go back for a second. Right, so we'll go to here, and here we can see that there was a we've got 129 number of lists in our circuits, number of circuits that were created. This one here has been cleared because you can see the zeros on there. As we go down, you can see that these circuits have been cleared as well. This first value is gone. That was the length of the circuit, but it's been cleared out. Very short ones. There's a fairly large one there. It's been cleared out. Some large, very short ones there getting cleared out. They've been cleared. There's quite a long one there. But it got cleared as well. That's quite a long one. Long circuit. It got cleared. And see, it's got a zeros at the beginning. It must have been almost complete. That's another long one there. It's been cleared too. See, it's got zeros at the beginning. And yet it's very close to this list here, this very short one. So this one must have been almost full, almost a full 1,000 in it. And then it got merged with another circuit. Probably a misoptimization on my part, that I always merged the second circuit with the first circuit regardless of their circuit sizes. But that's alright, it works, it's fine. Yeah, so there's my big list of circuits here. Okay, so let's do something interesting. Let's go back to this place, our list of distances, and let's enable this breakpoint, which is going to break before we sort our list. So I'm going to run this again, and we've hit this point, and you can see that this list is now not sorted. Right, we've got numbers, this number here, this number is bigger than this number here, and this one's shorter than that one there, so that's all just a mess. You can see these are all in sort of order that they were compared. Right, we're comparing E803 first to E807. Sorry, 03 E8 to 03 E7 to E6 E5. Right, probably going back to front as I usually do on my lists. And you can see it going down here. There's a lot. It's completely unsorted. And then we can see how quickly this gets sorted as soon as I run this again. Done. it's just done, right? If you take out the breakpoint, you don't even get to see that the list is not sorted in the time it takes to update the debugger. It just doesn't show up. Just doesn't change anything. Yeah. All right. So that's it for today. That's it for day 8. It was a fun day. This one took me a few days, I think, to actually get done in assembly, because like first I had to break it down into what am I doing. I'm making the junction box list. How am I going to structure this data in memory? Calculating the distances, right? Structuring that in memory. How I'm going to reference that back to the junction box list, and then writing a sort, and then doing the whole the final solution part as well. Right, I had to break it up into parts and solve it like that. All right, so yep, that was day 8. Next time I'm going to go over day 9, but I didn't complete day 9 completely. I did get the result out, but it's kind of a half broken solution, which wouldn't work for everyone. So I don't count it as a complete solution. But it's still kind of interesting to get into to see how badly I screwed it up, really. It was quite a difficult one, really. Day 9, yeah, day 9 was a hard one. And then after day 9 comes my redemption arc on day 2, which will be my live stream again. So, I hope to see you for day 9, same time next week, and then I will schedule when I will do the day 2 redemption stream. So, until then, I hope to see you next time, and I hope you enjoy assembly.